It's a pleasure to have Associate from ICT to visit us at Chatting University and give a lecture in search of a unified change. Professor Sen is undergraduate from Presidency College University. After that, he was at Kanpur. He did his PhD from Stonebrook and postdoc in Fermilab and SLAB. After that, he joined AI and in 95 he joined the National Research Institute. And after retirement, he moved to ICPS in Bangalore. Professor Sen has received innumerable accolades, and it will be difficult to get a list all of them. But maybe I should just list a few. He is a fellow of Royal Society. He got Padma Shri after that. Then he got his inaugural winner of the Extra Award, and then he got Padma Bhushan after that. Just to kind of make it a point. There are several other awards from ICT. I can just summarize it in just one sentence. There are two types of award winners. One type of award winner whose station goes up by winning the award, and there is a second type of award winner where the award section goes up when you receive the award. Professor Sen belongs to the second category where the station of the award goes up when he gets the award. Suffice to say that more from him, he was instinctively and I would like him to kind of introduce that topic to you.
Okay, thank you very much. Yeah, so it's a great honor for me to be coming to this university and giving a talk here. So when Dilip told me that I should give a talk, then I asked him who will be in the audience, and he said that you prepare assuming that people don't know anything. So I have prepared it that way, and I hope that it will not be too elementary for some of you. So the talk will be on the search of a unified theory of matter and fundamental forces. And as I go along, I will explain what the talk is about. Now, one of the goals of science is to discover the fundamental laws of nature. In particular, we would like to know, for example, what are the basic constituents of matter and what are the laws that govern their properties. And what I will try to do in this talk will be to describe what is known about this subject, what is not known, and how we attempt to know what is not known. So, I will begin by describing the modern understanding of the building blocks of matter. So, we take the most familiar material, water for example, which all of us are familiar with. Now, the crudest building blocks of water are the molecules, okay, which we call H2O. But as the name suggests, these are certainly not the most elementary building blocks. Each water molecule is made of 2 hydrogen atoms and 1 oxygen atom that you can see here. Now, once you probe deeper into the atoms, we find further structure. For example, we find that each atom is made of a central nucleus and then a set of electrons that revolve around it. So, the hydrogen atom, for example, has a hydrogen nucleus and a single electron around the hydrogen nucleus. Oxygen atom, on the other hand, has an oxygen nucleus and 8 electrons that revolve around the nucleus. Now, we can try to probe deeper, and when we probe deeper into the electron, we do not find any structure. So, we say that electrons are indivisible, okay, and we call them elementary particles. Okay. Now, I should emphasize that this is according to our knowledge today. Okay. This may change in the future, but as far as we know today, electrons are truly elementary because we have not been able to divide an electron. But for the nucleus, it is a different story. One finds that each nucleus is made of certain number of protons and certain number of neutrons. So, for example, the hydrogen nucleus is made of a single proton and no neutrons. Oxygen nucleus, on the other hand, has 8 protons and 8 neutrons. Now, we did not stop here, we can probe deeper into protons and neutrons, and we find further substructure. We find that protons and neutrons are made of even smaller particles, which we call quarks. So, for example, a proton is made of 3 quarks, okay, 2 of which are of a similar kind, which we call the U quark or the up quark, and a third one which is of a different kind, which we call the D quark or a down quark. Neutron, on the other hand, is made of 2 down quarks and 1 up quark. Now, we of course have probed the quarks also in further details, and so far we have not found any further structure inside the quarks. So, according to our current understanding, quarks and electrons are the elementary constituents of matter. However, it turns out that these are not the only elementary particles that we have in nature, because when we collide 2 very highly energetic elementary particles, we in fact produce new elementary particles. Okay. So, you take 2 electrons which are elementary, collide them at very, very high energy, and you find that what comes out is not electrons, okay, not even necessarily the quarks, but some new kinds of elementary particles. Okay. So, you have to add them also to the list of elementary particles that nature has. And later we will see the full list of elementary particles that we know today. Now, if we want to understand the properties of matter, okay, then of course it is important to know what the constituents are, okay, but it is also important to know what kind of forces operate between these constituents. Okay. For example, I can say that proton is made of 3 kinds of quark, okay, but if we don't know what kind of forces actually bind those quarks together, we will have no idea how to determine the properties of the proton starting from the properties of the quarks. So, we need to know what kinds of forces operate between these elementary particles, and that also has been studied in great detail. And today we know of 4 major kinds of forces that operate between these elementary particles. One is the gravitational force. Okay, this is the most familiar force to all of us. Okay, we feel it every day. This is responsible for Earth's gravity, the motion of planets around the sun, and so on. Then there is electromagnetic force. Okay, this again is reasonably familiar to most of us. It is the force of a magnet. Okay, if you take a magnet, we know that the iron, for example, gets attached to a magnet, and that is because of the electromagnetic force. Electromagnetic force is also responsible for the binding of electrons to the nucleus in an atom. Okay, without electromagnetic force, the atom will just fly apart into electrons and the nucleus. Now, at the subnuclear level, there are 2 other kinds of forces that operate. The strong force, this is for example responsible for binding the protons and neutrons inside a nucleus, or the binding of quarks inside protons and neutrons, etc. And then there is weak force. Okay, it is not directly responsible for any binding, but it is responsible for some kinds of radioactive decay. Okay, that is okay. It is responsible for many other things, but radioactive decay certainly is one of the important consequences of weak force. Okay, if we did not have the weak force, then we cannot explain why certain radioactive decays take place. And the way we measure them is by studying how the elementary particles scatter off each other. Okay. So, a typical experiment involving elementary particles, okay, involves taking 2 particles, accelerate them to very, very high energy, okay, collide them and see what comes out. Okay. And based on what comes out, we can study the forces that were responsible for this collision, okay, and in that process we may also discover new elementary particles. Okay, and we will see that these two aspects are intimately linked. Okay, the kind of elementary particles that we have also determine what kind of forces operate between these elementary particles. Okay. And for example, today the most high energy accelerator is the one that is based in CERN, okay, which accelerates particles to very, very high energy, collide them and try to see what comes out of that collision. Now, it turns out that even though gravity is the most familiar force to all of us, the effect of gravitational force between elementary particles is actually negligible compared to other forces. And to see this, one can just use some high school physics knowledge. Okay, one does not have to go beyond the high school physics knowledge. So, I will show why the gravitational force is so weak compared to other forces. So, here is a simple calculation. Let us take two protons, calculate the gravitational force between two protons and the electrostatic force between two protons and see what the ratio is. The gravitational force is given by Newton's law of gravity. Okay, so, G is a Newton's constant, Newton's gravitational constant, mp is the mass of the proton. So, because you have two protons, it is proportional to the product of the two masses, that is mp square, and gravity follows inverse square law. So, you divide by the square of the distance between the two protons. Electrostatic force is given by a similar formula, the Coulomb's law. Okay. We take the electric charge of each proton, take their product, okay, and again divide by the square of the distance between the two protons, because it also follows inverse square law. And in this ratio, you can see because both follow inverse square law, okay, r square term drops out, and what we are left with is just ratios that involve fundamental constants, the Newton's constant, the mass of the proton and the charge of the proton. So, you can put in the known values of these constants and one finds that the ratio is extremely tiny, it is like 10 to the minus 36. So, no experiment today involving elementary particles can actually see gravitational force between the elementary particles because the ratio is so small. And one can do a similar comparison between for the other forces and one finds that all other forces are also much larger than the gravitational force. So, this is so far descriptive. I have just given you a list of elementary particles and what kind of forces operate between them. But to really understand the physics of elementary particles, one needs a theory. Now, what is a theory? So, here is an example of a theory, okay, which again we learned in high school. Force equal to mass times acceleration, right. This is a Newton's law. What does it do? This formula tells us that given a particle of certain mass and given the force that acts on it, okay, it tells us what the acceleration that the particle feels, and hence it tells us how the particle will evolve as a function of time, okay, how the particle will evolve in time. So, a theory in a sense is some laws, some equations which tell us how a system evolves with time. In the same spirit, the theory of elementary particles will be a consistent mathematical framework that will describe how a set of elementary particles evolve in time. Okay, if we take two elementary particles, throw them to each other, okay, the outcome, okay, which is the time evolution of the system, should be predicted by theory. Okay, that is what one means by a theory of elementary particles. And if we have a theory, we can in principle use it to make prediction for the results of any experiments that involve elementary particles. Now, while developing a theory of elementary particles and their forces, one has to remember two important points, okay, and this is the reason why F equal to ma, that simple law, will not work here. The first reason is that in typical experiments, elementary particles move very fast. In fact, they move at a speed close to the speed of light, and because of this we have to use what is called the special theory of relativity that was developed by Einstein more than 100 years ago, okay, and that is the theory which works when the particles move at speed that is comparable to the speed of light. The second point that you have to remember is that the elementary particles are very, very tiny, and they are so tiny that measurement for them is a complicated process, okay, because when you try to measure the position of a particle, you disturb it, okay, and this disturbance, okay, you cannot ignore, okay, and quantum mechanics is a framework that tells you how to take into account the effect of the disturbance that you produce on the elementary particle when you try to measure it. So, this is the subject of quantum mechanics, okay, again developed about 100 years ago. So, you have to combine the theory of relativity and the theory of quantum mechanics to describe, to construct a theory of elementary particles, okay, and this framework is what we normally call quantum field theory. Okay. And this has this feature that when you collide two elementary particles at very high energy, it can actually produce other elementary particles. Now, fortunately, today we do have such a theory, okay, and this theory has been so successful that it has come to be known as the standard model. This theory is based on the principles of quantum mechanics and special theory of relativity, and in principle we can use this theory to calculate the result of any experiment that we wish to perform involving these elementary particles. And just to emphasize again that so far the standard model has been extremely successful in explaining almost all observed experimental data. But it has one major drawback, okay, and I will come back to this later, and that drawback is that it does not include gravity. Okay. Now, this is not an immediate problem for us today, because as you saw that in the physics of elementary particles, the effect of gravitational force is 10 to the minus 36 times the effect of the other forces. Okay. So, as far as measurements are concerned, okay, we cannot measure effect of gravity on the physics of elementary particles. Okay. Nevertheless, gravity will play an important role in what we are going to describe later. Okay. I have listed all the elementary particles that exist according to the standard model. These particles are divided into categories. Okay. The first category is quark. Okay. You may see up and down quark, which we introduced earlier. Okay. These up and down quarks are the ones which are inside protons and neutrons. Okay. But in fact, each of these quarks, okay, come in three varieties. Okay. I have called this 1, 2 and 3, but sometimes one also calls these colors, okay, red, blue and green. Okay. But those are just names. Okay. So, each quark comes in three varieties, okay, and then there are six kinds of quarks. Okay. So, there are altogether 18 of these quarks, okay, and each of these quarks also have their antiparticles, which are called antiquarks. Then you have the second category of elementary particles called the leptons. Okay. Here you will see the familiar electron, right. E stands for the electron, okay, but there are 5 more members in this family. So, electron is paired with a particle called electron neutrino. Okay. Then there is a muon paired with muon neutrino, and a tau particle measured with tau neutrino. Okay. And again each of these particles will also have their own antiparticles. The third category of particles, yes, nu, E and nu. What is?
What the nu E, nu suffix E.
Yeah.
What does that represent?
That's the electron neutrino. It's called electron neutrino, right. So, in terms of the symmetry group, right, if you think of this as transforming in a symmetry, in a 2-dimensional representation of SU2, E and nu E form a 2-dimensional representation of SU2. Okay. Similarly, mu and nu mu form another 2-dimensional representation of SU2. SU2, yes. Okay. So, SU2 is the weak interaction group. Okay. So, this third category of particles are what we call mediators. Okay. These are the ones which are responsible for these various forces that we introduced. Okay. So, the idea is that the reason that we have strong force, for example, okay, is because the quarks are continuously exchanging a kind of particles called gluons, okay, among themselves. So, we have 8 kinds of gluons, okay, which are producing the strong force. There is a single particle called a photon, okay, which is responsible for the electromagnetic force. Okay. Exchange of photon is the reason why 2 electrons are repelling each other electrostatically. And W plus W minus or Z are the 3 particles which mediate the weak interaction. Now, you notice that in this list, there is no particle that mediates gravitational force, right, and that is the sense in which I said that the standard model as formulated does not include gravity. Okay, there is no mediator of gravitational force in this list. And finally, there is a particle called the Higgs. Okay. This is not directly responsible for any of those major forces. Okay. Nevertheless, it is absolutely essential for the consistency of the theory, and in fact, it was predicted about 50 years before it was actually discovered. Okay. So, but we knew that without the Higgs, the standard model will just fall apart. Okay. Just the theory is not consistent. And in fact, many of the other particles in this list are also first predicted by theory and then later discovered in experiments. Okay. Because theory basically does not work. I mean, you cannot put arbitrary set of particles in the list and say that, okay, form standard model interaction out of these particles, right? It does not work. But despite its success, the standard model cannot be the final story, and there are some mundane reasons and there is some more serious reason. So, the mundane reason is that there are some experimental results which do not agree with the predictions of the standard model. For example, according to the standard model, the neutrino have no mass, but experiments show that neutrinos actually have a small but non-zero mass. Okay. When the standard model was formulated, everybody thought that the neutrinos really have no mass, okay, but it is only again after about 30 years after the formulation of the standard model, people actually discovered the neutrinos have very, very tiny mass. But these differences, these small departure from the prediction of standard model can be easily explained by a minor modification of the standard model without giving up any of the basic principles. Okay. So, here let me explain what we mean by without giving up any of the basic principles, okay, again by drawing an analogy. Okay. So, you are probably all familiar with the fact that the laws of gravity tells us that if we draw two balls, they will reach the ground at the same time, okay, because gravity is universal. But if you drop a ball of lead, okay, and say a ball of aluminum, okay, of the same mass and drop it, okay, and if you have a very accurate clock, the ball of lead actually falls faster. Why does it fall faster? Because you also have, besides the force of gravity, the friction of the air, okay, or the buoyancy of the air. Okay. These effects make the heavier, the more dense ball fall a little faster. But this does not require changing any of the basic principles, like F equal to ma, Newton's law is still valid. Okay. All you have to do is that in the expression for the force, you have to add some extra terms, okay, which is the law of, which is the force due to friction or the force due to buoyancy. Okay. So, these modifications that are needed to explain, for example, the mass of the neutrino are of that kind. Okay. You do not have to give up the principle of quantum mechanics, you do not have to give up the principle of special relativity, you just have to change the analog of the force laws a little more, little. Okay. So, that is the sense in which I said that these can be explained by minor modification of the standard model. But the more serious reason why standard model is not complete is because it does not contain one of the important forces of nature, namely the gravitational force. Now, as I have already emphasized, in all present day experiments, gravitational force between elementary particles is extremely small and beyond measurement. Okay. So, it does not have any direct conflict with something that you see in experiment, okay, except that the earth and sun of course have gravitational force acting between them, and if earth and sun are both made of elementary particles, right, then it better be that the elementary particles have gravitational force, because otherwise you cannot explain why the earth and the sun have gravitational force acting between them. Okay. So, that is the sense in which we have direct conflict with observation, but not at the level of elementary particles. Okay. As any complete theory has to account for all forces, however small they may be. So, let us try the easier things first, right. Can we modify the standard model so as to include gravity? Okay. After all, the neutrino masses were predicted to be 0 in the standard model, but it was not 0. So, why not just add gravity to the standard model, right? Just add another particle which mitigates gravitational force. To see why this cannot be done, we have to review again the principles of standard model. Okay, the standard model is based on the principles of special relativity and quantum mechanics. This I have already said. So, if we want to include gravity in the framework of standard model, we have to first make the theory of gravity consistent with these two principles, special theory of relativity and quantum mechanics. So, the first step, which is to make gravity consistent with special theory of relativity, this in fact was carried out by Einstein in 1915, and it led to what we call today the general theory of relativity. Again, at the time when general theory of relativity was formulated, it looked very esoteric. Okay, nobody thought that it will have any practical application in the future. Okay. But today, for example, the GPS system will not work if you did not have the laws of general relativity. Okay, the corrections that general relativity gives are absolutely crucial for GPS system to work. So, we do have a theory that combines gravity with special relativity. The hard part is the second step, which is to make gravity consistent with quantum mechanics. And this turns out to be an extremely difficult problem. Okay, and I will try to give a glimpse of why it is difficult. What are the main difficulties? So, the main difficulty comes from the fact that in Einstein's theory, the gravitational force between two objects is proportional to the energies of the objects. Now, you are all familiar with the fact that the gravitational force between the two objects is proportional to their mass. Heavier the object, larger is the gravitational force of the object. But in special theory of relativity, we also have this feature that energy and mass become interchangeable. Mass is energy and energy is mass. Okay, that is the famous relation E equal to mc square. Okay. So, this means that the gravitational force between two objects which are moving at very high energy, which have very high energy, becomes larger and larger. Okay. Even if there are two electrons, okay, they have very small gravitational force. As the two electrons become acquire larger and larger energy, the gravitational force starts increasing. Due to this increase in force with energy, okay, one finds that the answers to sensible questions turn out to be infinite. Now, this clearly is not a sensible answer. Okay. For example, if you want to ask, you collide two electrons, okay, what are the chances that you will find two electrons coming out at 30-degree angle? Okay. Within standard model, there is a well-defined answer, you can calculate, okay, what fraction of the time two electrons will come out at 30-degree angle. Once you take into account the effect of gravity, okay, and you try to naively do what you do in quantum field theory, which is the combination of quantum mechanics and special relativity, we find that this answer turns out to be infinite. This clearly is not a sensible answer. Now, this may seem surprising because I told you that the gravitational force is extremely tiny, right? It is 10 to the minus 36 times the electromagnetic force. So, how can it suddenly become so large? The point is 10 to the minus 36 times infinity is still infinity. Okay, that is the main point, that however small the gravitational force is, okay, the theory, okay, when you just naively apply the techniques of quantum field theory, you find that you get infinite answer for sensible questions. Okay, it is a tiny number, but multiplied by infinity. So, this is what we know today. Okay. Now, we are going to discuss how to explore the unknown, right? How to go about trying to find a theory of gravity that is consistent with quantum mechanics, okay, and which you can possibly incorporate within the framework of the standard model and get a theory of all particles and their forces. So, this is where string theory comes in, okay, and that is the subject that I work on. This provides a possible way out of the problem. Okay. It gives a sensible quantum theory of gravity. And as you will see that it also could provide a possible way of combining a theory of gravity with the theory of elementary particles. But I should caution that this is still work in progress. Okay. So, from whatever I say from now on is something that is still work in progress. Okay. It has been in progress for many years and there have been lots of developments, and I will try to describe some of these developments in the rest of the talk. So, the basic idea in string theory in fact is very simple. It tells us that different elementary particles, okay, which you think of as point-like objects, are in fact not point-like objects. They are just different vibrational states of a string. So, if string theory is correct, then in some sense it unifies all different kinds of elementary particles. Yes, these are closed, but there are also some cases you can also have open strings, right, with two ends open, okay, but closed strings are the most common ones. So, I will be focusing on the closed ones. So, you take a string with ends, no ends, okay, and the idea is that as the string vibrates, okay, it can exist in various vibrational states. It can vibrate, for example, in a radial mode, right, or it may have the first harmonic or the second harmonic, and then each of these can have various kinds of amplitudes. Okay. And once you pass it through the machinery of quantum mechanics, okay, one finds that each of these vibrational modes, vibrational states actually behave like an elementary particle. So, if string theory is correct, okay, then all the elementary particles that you see, the electron, muon, neutrino, quarks, photon, right, all of them will just be the different vibrational modes of this string. Now, the first question that one would ask if one sees this proposal is that if this is the case, why have not we seen this, right? I told you that electrons, right, you have probed electrons, right, and it looks like particles, right. So, why have not we seen the structure of electrons as strings if this is really the case? And the answer to this is actually given within string theory. One can estimate the typical size of a string, okay, and one finds that it is really extremely tiny, it is of the order of 10 to the minus 33 centimeter. And this is much smaller than any length scale that you can probe in a present day experiment, right. Present day experiments can see a distance scale of the order of 10 to the minus 17 centimeter. Okay. We can say that the most powerful microscopes that we have today have a resolution of order 10 to the minus 17 centimeter. Okay. So, thus just like a particle of dust, right, to us to naked eye will look like a particle, right, even though clearly that has a structure. Okay. In the same spirit, we can say that to a present day experimentalist, the state of the string will appear to be particle like objects, because even if string theory was the correct theory of nature, okay, the strings will actually appear as particles with the current resolution of the microscope that we have. Yes, it is predictable calculus in itself, the size is 10 to the minus 30 centimeter. Now, so we need to formulate a theory of strings consistent with the principles of special relativity and quantum mechanics, because these are the foundations of our modern understanding of nature. And what one finds is that just as a consequence of these two requirements, strings automatically exert gravitational force. Okay. So, in other words, one of the particles, right, I told you the strings can exist in various vibrational states. Right. One of those vibrational states, okay, has exactly the property that a mediator of gravitational force will have. Okay. So, string theory in a sense gives gravity for free. Okay. In the theory of elementary particles, as you saw, it is hard to incorporate gravity, right, because you get infinite answers. In string theory on the other hand, it is hard to get rid of gravity. Okay. Once you have a string theory, you have gravity. So, this is one of the main reasons why people are excited about string theory, okay, that this seems to be not only that it gives a consistent order to quantize gravity, but gravity is very natural in this theory, right? It's hard to get rid of gravity. Now, gravitational force still grows with energy because it's of course consistent with the Einstein's theory of relativity. Okay. But what happens is that energy now is smeared over the string. Okay, instead of localized on a particle, okay, that like if you have a very high energy electron, right, energy is localized on the electron. If you have a very high energy string, the energy is actually smeared over the string, okay, and because of this smearing, okay, the answers to sensible questions now turn out to be finite. Okay, all the problems that we had in the theory of point particles go away in once you use the theory of strings. But there is a price to pay. The price to pay is that in string theory, the laws of string theory are completely constant. I gave you some example earlier. Okay, the ball of lead and the ball of aluminum, okay, don't fall at the same speed, and you explain it by saying that the laws are actually slightly different, right? It's not just the law of gravity, but there is also some additional force. In string theory, there is no freedom of adding any additional force or adding any additional particle. Okay. Once you have committed to having a theory of strings, okay, the laws are so tightly constant that you either get what you want or you just have to throw away the theory. Okay. You just can't say that, okay, it doesn't work, so let's change the laws a bit. Right. That's not possible in a theory of strings, okay, whereas that was possible in a.
By the theory itself.
Yeah, all the laws are put by the theory itself. You are not putting anything. You cannot do anything with the laws. Okay. So laws are given once and for all. There is still some freedom that we will see, okay, where the freedom is, but the laws are absolute. Right. You cannot change the laws. For example, we cannot demand that the dimension of space is what we see in nature. Right. We are all familiar with the fact that we are living in 3 dimensions. Right. We have left and right, front and back, and top and down. Okay. In string theory, you cannot just say that, okay, this is where we start. Okay. We start assuming that we are living in some d dimensions and determine d by the consistency of the laws. Or we cannot even demand that the different vibrational states of the string behave like the elementary particles you observe in nature. Right. We would like to have one of the vibrational states representing the electron, right, another one representing the quark, okay, up quark, another one representing the down quarks, and so on. But this is not something that you can demand of the theory. Okay. You have to just see if the theory gives you that. One thing is for sure that it gives you graviton, right, because gravity is hard to get rid of in string theory. Now, after some detailed calculation, one finds that in string theory the dimension of space is 9. Okay, there are 9 space dimensions, and often one adds one extra time. Time is always there, right? So one sometimes says string theory lives in 10 dimensions, right? 10 space-time dimensions or 9 space dimensions. Now, 9 dimension may be hard to visualize, right? Or not for a mathematician, but for physicists, right? I mean, what do you mean by 9 dimensions, right? And the way, I mean, I don't know, probably even the mathematicians don't view 9 dimensional as a geometric picture, okay? But the standard way to visualize 9 dimensions is that in 3 dimensional space you need 3 numbers to specify a point. Right? In 9 dimensional space you will have to specify a point by 9 numbers. Right? That's the way you should think of a 9 dimensional space. Okay? Use the language of coordinate geometry. So mathematically there is no problem in describing a 9 dimensional space. Okay? The problem is that this is not what we see in nature. Okay? So how can string theory be relevant for what we see in nature? Because in nature we certainly see 3 dimensions and not 9. Now it turns out that there is a simple idea, okay, that can actually make the 9 dimensional space appear as if it is a 3 dimensional space. Okay. And this idea is what is known as compactification. Okay, and I will try to explain this idea of compactification with the help of a simpler example. Okay. So we will take a 2 dimensional space, okay, and describe geometrically how the two-dimensional space can be made to appear as if it is a one-dimensional space. Okay, and then the same mechanism can be generalized to make a 9-dimensional space appear as a 3-dimensional space. So, let us imagine a 2-dimensional world, right, like the floor of this room, okay, extended in infinite directions, extended infinitely in both directions. That is a 2-dimensional world, and you can imagine creatures living on this 2-dimensional space. But now, let us change this a little bit. Take the same 2-dimensional space, but imagine that it is the surface of a cylinder. Forget about the interior of the cylinder, okay, that does not exist. Right? Imagine that this 2-dimensional space is the surface of a cylinder, okay, which means that you go, suppose the cylinder radius is r, okay, you go 2 pi r in one direction and you come back to the original point. Okay, that is what you mean by taking this 2-dimensional space to be the surface of a cylinder. Imagine an ant living on this 2-dimensional space, ant starts walking along the cylinder, and after some point it will come back to where it started. Now, in this imaginary 2-dimensional space, okay, if the radius is very, very large, okay, imagine that it is larger than the range of the most powerful telescopes that these 2-dimensional creatures have. Okay, then to them it will look like a flat 2-dimensional space which is flat in all directions, which is infinite in all directions, because they have no way of knowing that if you walk 2 pi r distance in one direction, you actually come back to the original point, right, because you cannot even see that far. Right. If you could see that far, then you will see an image of yourself, right, because light also travels along the same surface and you will come back to the original point. Okay. So, if r is very large, then the 2-dimensional space will appear to be infinite in both directions. But now consider the opposite situation where r becomes very small, okay, and you can see that this world, a world of this kind, will start looking more and more one-dimensional. Right. If you are far in the back of the room, right, it may look like a line, right, instead of a 2-dimensional surface. And one can make it more precise, okay, that if r is smaller than the resolution of the most powerful microscope that these 2-dimensional creatures might have, okay, then the world will appear to be one-dimensional to them. So, when today we say that we are living in 3 dimensions, that only means, okay, that we have 3 large dimensions, okay, but experiments today cannot, or any observation cannot rule out the possibility that there are some additional dimensions in our world, right, whose size is less than 10 to the minus 17 centimeter, because 10 to the minus 17 centimeter is the resolution of the most powerful microscope that you have today. Okay. So, if there are additional dimensions in our world which have size less than 10 to the minus 17 centimeter, then you would not know about it in today's experiment. So, the same idea essentially works in making a 9-dimensional space look 3-dimensional. So, you take 6 of the 9 space directions to be small that describe some compact space, and when the size of this compact space becomes sufficiently small, then the space will appear to be 2-dimensional. So, according to string theory then, our space has 3 large dimensions and 6 small dimensions. So, this is the way string theory can be made to make peace with what you observe today. Does not mean that that is the right theory, okay, but at least it is not inconsistent with what you observe today, because while string theory tells us that our space has 9 dimensions, okay, it does not tell us that all those 9 dimensions have to be large. Now, it turns out that there are many different compact spaces K that one can use for compactification, okay, and in here in fact this is the subject in which string theory makes connection to mathematics, okay, because many of these compact spaces which are useful for physics turn out to have been discovered by mathematicians. These are called Calabi-Yau spaces, okay, and based on those Calabi-Yau spaces one finds that you can actually come pretty close to what we actually see in today's world. So, what this is saying is that even though the laws of string theory are the same, once you compactify some of the dimensions, then there are various possible realizations. And these different possibilities, okay, there are different ways of thinking of these different possibilities. Okay, let me give you a simpler version and then we will go to this more complicated version. Okay. One way to think of this is that even though the laws are the same, okay, they are just different solutions of the same theory. Okay. Imagine that you take Newton's law of gravity, okay, or just on the surface of the earth. Okay. It says that the force is equal to mg times mg, okay. So, it moves at constant acceleration. But that does not mean that all solutions of these equations are the same. You can drop a particle from here or drop a particle from higher point, okay, drop a particle with some velocity, okay, and all those will describe different kinds of motion of the particles. Okay. We say that they are different solutions of the same theory. Okay. So, in that sense, these different choices of compact spaces you can think of as different solutions of string theory, even though the laws are fixed once and for all. But another viewpoint which is also very useful is to think of them as different phases of the underlying string theory, okay, and I will try to explain what we mean by different phases. This is again best illustrated by an analogy. Consider H2O molecules, right, this is where we started. Okay. Suppose somebody gave you a theory of H2O molecules, okay, the H2O molecules, all kinds of whatever forces act between these H2O molecules, suppose somebody has given you a theory. Okay. But based on that theory, okay, we have different realizations because ice, water and steam, okay, all follow the same laws. Okay. Ice, water and steam are all made of H2O molecules. It is not that the molecules of ice have different force acting between among themselves as the molecules of water or the molecules of steam. We call them different phases of the theory. In the same spirit, these different compactifications of string theory, different choices of the compact space can be thought of as different phases of string theory. And just as the environment inside ice, water and steam are very different, right, even though as I said, the laws that describe the force between the molecules is the same in ice, water and steam. But clearly the environment inside ice is very different from the environment inside water, right. Fish lives in water but not inside ice. So similarly, the 3-dimensional environment for different choices of the compact space K will be very different in string theory. Now, it turns out that for some choices of this compact space, the 3-dimensional environment is very similar to what you observe in nature. Okay. So, what we mean here by very similar is that it has elementary particles and forces similar to what you observe. Okay. So, as I have already said, and let me emphasize again, okay, in all of these cases you have gravity, right. Gravity is an integral part of string theory, but for many choices of these compact spaces, you also have forces like the weak force, the strong force, the electromagnetic force, particles like the electrons and quarks and so on. And this is what gives us hope that perhaps string theory can not only describe gravity, but also all other forces and all the elementary particles. Challenge, however, is to find
Exactly the elementary particles. You are thinking them as strings again.
yes, yes. But exactly mean exactly up to the experimental accuracy that we have, right. So, electrons for example, right, there is some, it will be a string, but today we do not see the string structure, right. The properties that we will study should be exactly what we see in experiment today, right. So, that is the main goal of the subject, right, to find a phase of string theory that gives exactly what we see today, right. What we have achieved so far are discovery of phases which come close, but not exactly what we see, okay, and that is the main challenge of the subject. We can in fact push this analogy a bit further. Suppose you are living inside water and you want to study properties of ice. Could we do that? We can, because we can just freeze a big block of ice, block of water into ice, and we can study properties of ice. It turns out that we can also do something similar with the phases of string theory. So, here is an example. Okay, this is an extreme example. Okay, I have just chosen the numbers arbitrarily so that it's extreme. Then imagine you are living in a phase where 6 of the directions are circles of circumference 10 to the minus 24 centimeter. Okay. 10 to the minus 24 centimeter is certainly much smaller than what we can see today, right. So, in that case, it will look like the space is 3 dimensional, okay, because the extra dimensions are all small. Now, you can ask, is it possible to create a large region just like we created ice inside water? Is it possible to create a large region inside which the size is 10 to the 10 light years? Okay, again, I have chosen this number at random because 10 to the 10 light years is basically at the border of what we can see, how far we can see today. And it turns out it's possible, right. In fact, within string theory, you can construct such configurations that even if you are living in a phase where the extra dimensions are very, very tiny size, okay, if you had sufficiently high energy, okay, we can produce a configuration, okay, where you will have a big blob in which the radius will be very, very large, okay, so large that it will be indistinguishable for us from living in 9 space dimensions. So, the collection of all the phases is what is known as the string landscape. Okay. So, if string theory is the correct theory of nature, then we must be somewhere in this landscape. Okay. The problem is that we do not know where, okay. But that's the goal, right, to find where we are in the landscape. So, the problem of connecting string theory to nature can be summarized in these 2 sentences: find our place in the landscape. Okay, we search in this whole space, where are we, right? Which point in this space of string phases, okay, actually describe the nature that we see. And the second, we have to explain why you are there, right? Imagine that you have identified a point in this landscape, okay, where everything works. You get the correct mass of the electron, correct mass of the quark, correct mass of the muon, and so on. Okay. Nevertheless, somebody will ask, why that point? Why is that special? So, the possible answer to the second question, in fact, is already inherited from what I described earlier, and that is that maybe no single phase of string theory is special. In our universe, we know that some place we have water on the surface of the earth, but there are other places where there is ice, right, because the temperature is too low. We do not ask why there is water on the earth and ice on somewhere else, right. It is just the environment is different. So, the idea is that maybe different parts of the universe exist in different phases, okay, that the actual universe we see is a tiny part of a very big universe. Okay. In our part of the universe, we are living in one phase, maybe in different parts of the universe, we are living in some other phase. And this is what is sometimes called the multiverse. Okay. So, I have introduced 2 words and sometimes they are exchanged, okay, but let me just emphasize that these are 2 different things. Landscape, okay, is real, okay, it just says that there are many, many phases of string theory, okay, and that is the string landscape. Okay. Multiverse is the idea that all of these phases are realized inside our universe, okay, in different regions. That all of these different phases are realized in our universe, but in different parts, right. So, again coming back to the water molecule, right, there are clearly at least 3 phases of water: steam, ice, and water. Okay. Then the second point, okay, which is also true, is that we can have a big reservoir, okay, where part is in ice, part is in water, and part is in the form of steam. Okay. Whether our universe is of that kind, we do not know, right. That is the idea of the multiverse, that the multiverse says that actually different parts of the universe are in different phases. So, this is more or less the end of my talk, okay, and this is what I will call the main story of string theory. Okay. But just like the great epic, string theory also has many side stories, okay, and these involve applications of string theory to solve problems in other related fields. Okay. One is understanding black holes in quantum theory. Okay, I will not say anything more about this. This is a whole talk by itself. Then string theory problem, approach to solving problems in the theory of point particles. Okay, this again is a big subject. String theory applications to mathematics. Okay, this maybe I can say a few words. Okay. So basically, I said that the string theory laws are completely constrained. Okay. But even within those constraints, right, it's not apparent that it's really a consistent theory. Right? This has a lot of constraints. Okay. And the idea and the point is that you calculate, you take a given process, take collide two particles, ask what is the probability that the particles will come out as 30 degree. Okay. There are different ways of doing this calculation. And it's not obvious that these two different ways of doing this calculation will give the same answer within string theory itself. Okay. Mathematically, they give two different looking expressions. Okay. So this says that if string theory has to be consistent, then these two expressions that we get for the same quantity calculated in two different ways better be the same. Okay. And this leads to new kinds of mathematical identities, okay, and some of which were in fact not known at the time when they are discovered in string theory, and they are only verified by the mathematicians later.
Two particles come.
Yes.
Strings,
Yes.
different phases.
Two particles in different phases are hard to come, right? Because, yeah, same phase. Yeah, take a given phase.
Then it is relatively easier to compute if they are different phases. It's not possible.
In different phases, the point is, see, the particles themselves may not exist. Suppose you have a particle coming inside a phase like water. Once it enters the ice, it may not even exist in that form. Right? So these kinds of questions you ask within a given phase. Take a given phase of string theory, take a particular Calabi-Yau space, okay, and in that space you ask, if you collide two particles, what is the probability that they'll come out at 30 degree?
Computation possible?
Computation is possible, right? And there are different ways of doing the computation. And it's not a priori guaranteed that those will give the same answer. If the theory is consistent, it better give the same answer. Okay? But this leads to new kinds of mathematical identities, right? Because mathematically they look like different expressions. Okay? And by requiring that those two are the same, right, you get new identities, and then the mathematicians can go and verify whether those are really true or not. So that's the way string theory makes connection to mathematics, that it actually produces new identities in mathematics based on the consistency of the theory. Well, we don't know at this stage, right? It could be some people claim that it's infinite, some people claim that it's very small, right? So we really don't have much idea, right? Because some of the phases can be studied well, okay? Only a finite number of such phases have been found, right? But beyond that, how many more phases are there, we really don't know at this stage. Yes.
What will happen in case of vitreous ice or when the water is just about to turn into steam? The particles will change and they will go into different phases, right?
Yes.
At that time, how is the communication possible? How do we actually connect the particles in that?
Yeah, so it's very hard typically, right? If you take a particular kind of elementary particle in one phase and suppose it's crossing over to the other phase, right? It will completely lose its identity. It will become some, that process is very hard to study in this subject, right? But it certainly will not remain like a particle. So imagine that you take an electron, okay, and throw it into some other phase, right? It will completely lose its identity, right? Because electron doesn't even exist in the other phase, right? It's some completely different kinds of elementary particles. Okay, so let me now summarize. Okay. So what I have tried to describe in this talk is the story of string theory. As we saw, string theory is an attempt to formulate a theory of elementary constituents of matter. It's based on a very simple idea that different elementary particles are different vibrational states of the string. We saw that it provides us with a consistent quantum theory of gravity, okay, and possibly of other forces. Okay. This depends on our ability to find a point in the landscape that describes exactly what we see in nature. But this is still a challenging problem, that is to find the phase of string theory that describes the world around us. Okay, and this is where the subject stands today. Thank you. Yeah, there are there are fermionic strings, right? Without, I mean, certainly there is no problem in having the theory without supersymmetry, right? But it's just control is less. The computational control is less. Yeah, it's certainly possible to have. Yeah, you don't need supersymmetry to have fermions or anything in string theory. Each particle. Yeah, it can change in, for example, a given kind of string. Right? Imagine a string is vibrating in some state. Right? It can break apart into two other strings vibrating in another state. Right? And that will be interpreted as a particle breaking up into two other particles. Right? We know, for example, if you take a muon, right? Muon can go into an electron and an electron antineutrino and a muon neutrino. Okay? So, one particle breaks apart into three particles of different kinds. Right? These we describe in string theory as a string existing in some modes of vibration breaking apart into some different modes of vibration. Yes, so each particle will have a unique pattern in string theory. Yes.
I just solved a problem previously, couple of years back, that the ambiguity of the string theory and using the string field theory, right?
Yeah, so string theory is completely unambiguous, right? You can get completely finite answer to all amplitudes, right? That is certainly true.
My question is that, like, sir, when you discovered this, so that was not entirely input data, it's a lesser input data was there, and you solved this somehow. Does it mean that this data is not fully, this theory is not fully independent? If it's not, how it's affecting the unification problem?
See, the theory is, as I described, this theory is completely self-contained, okay, and the laws are fixed once and for all, right? You cannot change the laws. What you can change are the solutions or the phases, because given the laws, there are many different realizations, which are these different phases of string theory, right? And the only way it can solve the unification problem is to find a particular phase which has gravity plus all the other forces and all the other elementary particles. Okay? So that's the only way it can solve the unification problem. I'm not sure if that's the question you asked or was it something else?
Still working on this, that's why it's not fully published.
I see. Okay.
Any other question?
Sir, my question is kind of simple. Is there any visualization model for the where you explained that the 2 dimension can be converted to 1 dimension?
Yes.
Is there any specific visualization model where the 9 dimension is converted to 3 dimension or something?
Well, I don't know visualization. It depends on your ability to visualize a 6-dimensional space, right? The simplest one is you think of 6 circles, right? You have you have one circle like this, one circle like this. So a 2-dimensional torus, right? That's like the product of 2 circles, right? There is a circle like this and a circle like this. Okay? That you can generalize, right? 6 circles. That's the simplest one. Some people can maybe visualize also Calabi-Yau spaces, right? Which are 6-dimensional complicated spaces, but I certainly cannot, right? But the point is that you can do a lot of, to work with Calabi-Yau spaces, you don't really need to visualize it, right? You can use the idea of coordinate geometry. You write coordinates, right, and write equations, and then you can get all you want by solving those equations, right, without actually visualizing how the Calabi-Yau space looks like. But it can help. I mean, sometimes if you can visualize, maybe you will get better insight, right? I am not saying that it's not important, but I certainly cannot do it.
I have a very non-physics kind of a question. This is my first full physics lecture ever in life.
Okay.
So, two questions actually. One is about, I thought when you were talking about the movement from the older particles kind of talk to the string kind of talk, you have moved away from describing particles as fundamental and instead describing something else as fundamental.
Yes.
You can derive from
Strings,
particles.
yes.
But then later I see you talking about strings with the same kind of constraints with which we talk about particles, dimension, visualization. So I was not sure why you brought the particle kind of imagination from the back door after taking it away.
Yeah, so the point is, okay, the reason for that is that we really cannot visualize dimensions from the string viewpoint, right? And if the dimensions are large, right, it's good enough. I mean, you can just think of the dimensions as you are familiar with. Okay? The problem comes when the dimensions become small. Okay? When the dimensions become small, then you are absolutely right that then the notion of geometry, right, as you know, breaks down completely because you are really probing by strings, not by particles. Okay? So imagine that your probe is a tiny string. Okay? If what you are probing is very big, then it doesn't matter whether the tiny string is a string or a particle, right? So for large dimensions, it doesn't matter. For small dimensions, it does matter. Okay? In fact, one of the features that come out of string theory, right, which is not a property of particle physics, particle theory, is that if you start reducing the dimension to be smaller and smaller, imagine that you take one direction to be compact and start making its dimension smaller and smaller. What you find is when the dimension becomes smaller than the string size, right, which is 10 to the minus 36 centimeter, it actually becomes larger and larger. Okay? That's something that comes out of string geometry. Okay? It's not a property of a particle geometry, but that's where it differs. Okay? So I am using this language of dimensions, right, only in the sense that we visualize things better in terms of dimensions, right? And as long as the dimensions are large, it's still okay.
The status of the kind of thing that a string is, like I do understand between medium-sized objects like this and the smallest object particles you described, one could still imagine, okay, these are objects.
Yes.
Smaller and smaller. What is a string? It is not an object.
String is an object, it's an object, but it's a one-dimensional object, right? It's a string that I drew, right? It's a string, it's a one-dimensional object without ends. Right? That's the object with which you probe everything. See, in string theory, you cannot introduce particles, right? So the normal concept of geometry is based on point particles, right? Geometry you think of as a collection of points, right? Manifolds and various other things you define in terms of points. That notion breaks down in string theory, okay, unless the size of the space that you are considering is larger than the string size. Okay, once the size becomes small, comparable to string size, then you have to use completely different kinds of geometric description, right? That I didn't go into that. Okay. So if you are confused by the fact that I am using the same notion that we use for particles, right, it's only because I was thinking of dimensions to be larger than the string size. Okay. Once the dimensions become comparable to the string size, then you have to really change the notion of geometry altogether. Yeah.
Is there any stark wall on the how small the weight of a particle can be? Like, can there be a particle which weighs 10 to the power minus 20?
Yes, a photon has no mass at all, right? So there is no lower bound because photons and gravitons, non-zero mass, no, at least from string theory there is no lower bound that we know of, right? It could be as very light.
And I mean, in string theory, let's say other dimensions, then the one we can observe, can there be like, can the speed of light vary? Can the absolute temperature can go beyond 0 Kelvin? I mean, lower than 0 Kelvin. Can some things happen?
Yeah, see the point, these are in some sense part of definition, speed of light. Let's take that example, right? One uses the speed of light as the unit. See, a dimension full quantity, right? You cannot say whether it varies or not, right? Because then what it varies with respect to what? Right? So what you do in physics is that you use the speed of light, the Planck's constant, okay, and Newton's gravitational constant to set the units of length, mass and time. Okay. In terms of that, you can ask about other things. Can they vary? Right? And they can vary. Okay? In different phases, of course, all these other things will vary. Right? But the speed of light itself, to say that the speed of light varies, it's not very meaningful because speed of light is used to set the units. Right? You have to calculate the ratios which are dimensionless, right? And then you can ask if that varies or not.
And for the, let's say, temperature, can the temperature be lower than
Temperature is somewhat of a derived concept, right? I mean, even you don't have to need even string theory, right? I mean, there are examples where you can create population inversion. See, temperature means what? That higher energy states are less populated than a lower energy state, right? That's what that's the thermodynamic concept. That the probability of populating higher energy state is smaller than the lower energy state. Negative temperature means it will reverse, right? And you can actually create systems in lab where such population inversion takes place, right? The higher energy states are more populated than the lower energy states, temporarily, right? You can describe that as a negative temperature. Okay? So you don't even need to go to the other phases or other dimensions to have negative temperature, right? Because it's really, I mean, temperature is a derived concept, right? That it's not a fundamental constant or something. This is.
Has there been cases that in lab less than 0 Kelvin been achieved?
If you call this less than 0 Kelvin, right? That population inversion, right? You take a level of two systems. Yeah, I think less than 0 Kelvin is I mean, as I said, temperature, the way you define temperature, right, is that for energy E, the probability is e to the minus C over kT. Okay. Now, if higher energy states have higher probability of occupation, that is like negative temperature, right? It is no distinction, I mean, there is no distinction between that state and a state with negative temperature, right? Because if T is negative, then higher energy states will be more populated, right? E to the minus C over kT will be larger for higher energy than for lower energy. But see, that is the way you define temperature in a fundamental sense, right? We think of temperature as, okay, you touch a body and how hot it feels, right? But the way you define temperature in thermodynamics or statistical mechanics, right, is through this probability, that a state of energy E will have probability to the minus C over kT of occupation. Right? So, to make negative temperature system, you just have to reverse this ratio. Right? The point is, if you have a big system with many levels, okay, then making this inversion is very hard. But temperature can be defined even for two-level system, right? Imagine that you have an atom with two energy levels, and you have a collection of many of these atoms.
Some plus delta Kelvin to, let's say, minus delta Kelvin. In this case, there will be this, it will also come to this 0 Kelvin.
Yeah. Yeah. See, the point is that you think of really this as 1 over T as the correct variable. Okay. In terms of 1 over T, it's either positive or negative.
Yeah.
Okay.
So if T is 0, then it becomes
infinite. Yeah. Yeah, exactly. So, infinite temperature means all states are equally occupied, right? Because then e to the minus C over T is the probability, right? So, E does not matter. Sorry, I think I am saying something wrong, yeah. E to the, yeah, if you think of 1 over T as a function of 1 over T, it is continuous. E to the minus C over T looks discontinuous as a function of T, but as a function of 1 over T, it is a continuous function, right?